Thank you very much for the opportunity to talk about our results. So yes, I will tell about trying to address the question of relativistic and QED effects in many electron diatomic molecules, where these molecules are still small from the point of view of the chemistry, but they are much larger than hydrogen molecule. I think that after these two talks of Michał and Mariusz, there was perfect introduction to my talk, because I'm exactly in the middle with the size of the systems that are interesting for me and that we study in my group. So first of all, I would like to mention that the work I present was realized with my postdoc, Marcin Gronowski, my PhD student Sangami, and my master student Adam Koza. So we are working at the University of Warsaw, and we study mostly ultra-cold molecules, or we call it in general quantum molecular systems. So before I will present the results, I would like to mention briefly what we are doing. So on one hand side, we run accurate ab initio calculations for small or medium-sized molecules with the direct application for cold and ultra-cold physics and chemistry experiments. We are very much interested in collisions and chemical reactions, especially controlled chemical reactions. We are also looking on the formation, dynamics, and control of ultra-cold molecules. And we also study few body and many body quantum dynamics of the systems, or the implications of the atomic molecular structure and collisions for many and few body quantum physics. Okay, so after this introduction, I would like now to justify, maybe before I will present the results, why ultra-cold molecules are so interesting and why do we study them. So with ultra-cold molecules, we can realize controlled collisions on controlled chemical reaction. In fact, achieving the full quantum control. So it means that we can prepare, for example, reagents in the fully controlled quantum state and have full control over what's going on. And hopefully this kind of experiments will give us better understanding of chemical reactions at other conditions as well. On the other hand, once the systems are really cold, lots of noise and uncertainties is heavily reduced. And this opens the way for precision measurements similar to precision measurements with hydrogen molecules presented a moment ago. And these highly accurate measurements, highly accurate spectroscopic measurements with cold molecules can also be used for testing fundamental laws of physics. Then we can use ultra-cold gases of molecules to study many-body quantum physics as well, or quantum simulation, where, for example, we can try to understand some complex many-body systems by a bit simpler systems that we can realize with cold atoms or molecules. And at the end, there are also some proposals and first attempts to realize quantum computing, or in general quantum technologies with cold molecules. So in my talk, I will be addressing mostly the two first points, where we are interested in systems that are prepared for controlled chemical reactions, but at the same time they potentially can be used for precision measurements. And the question is, can we also somehow use ab initio theory to have accurate enough calculations for systems a bit larger than hydrogen to contribute to this kind of research? So we selected two molecules to present now. So one of the molecules is sodium-lithium molecule in the lowest triplet sigma state. So this is 14 electrons. So of course it's much larger number of electrons than hydrogen molecule, but it's, from the chemical point of view, it's not huge molecule. In the triplet state, it's weakly bound van der Waals complex because this is the spin polarized. These atoms are spin polarized, so really there is no proper chemical bonding, and the interaction energy is very low. The triplet state that we consider here is the lowest energy excited state, and in fact is the lowest energy metastable state because the ground state of the lithium-sodium molecule is the singlet state. And maybe what is the most important and the motivation for selecting and using these molecules is that in the triplet state, this molecule is both polar and magnetic. What do I mean by this? I mean that this molecule has both electric and magnetic dipole moments, and this makes it perfect for quantum simulations of many-body physics that can be realized in cold experiments. And these molecules now are investigated experimentally at the group of Professor Ketterle at MIT. On the other hand, we consider aluminum fluoride molecule in the 2 electronic states, in the ground singlet state and the lowest triplet pi state. So aluminum fluoride molecule is a bit larger, it's 22 electrons. Still, it's rather small molecules, but it has completely different chemical nature than lithium sodium because this is deeply bound covalent molecule with very strong chemical bond. These two states that we consider, one of them is the ground state and the second one is the lowest energy excited and metastable state with relatively long lifetime. And what is the most important about aluminum fluoride molecules is that it has highly diagonal Frank-Condon factors between this and other electronic states, and this makes it perfect for laser cooling. In other words, I would say that aluminum fluoride molecule is the molecule that is the most similar to atoms among all molecules that we know. And this opens the way to employing different methods of atomic physics, of ultra-cold atomic physics that was developed and used for atoms to apply directly to molecules like this and realize new exciting experiments. And the experiment with these molecules is realized at the Max Planck Institute in Berlin in the group of Dr. Truppe. And we have some collaborations with both of these groups. So just giving brief status of the experiment. So with the sodium lithium molecules, it was already produced experimentally 3 years ago by the stimulated adiabatic Raman passage, starting from the magnetoassociation of cold atoms using Feshbach resonance with the stimulated coherent transfer through the excited triplet state. The molecules in the lowest rovibrational level of the ground triplet state was produced. And next, several different experiments on the spectroscopy of this molecule, including accurate spectroscopy of all vibrational states in the ground state and in the lowest triplet state were realized. But having these molecules, they also started investigating more exciting physics and chemistry, like, for example, this year, for the first time, the sympathetic cooling of the lithium-sodium molecule in collisions with sodium atoms was realized and published in Nature a few months ago. And also they have now new results where they observed controlled with the magnetic field collisions and chemical reactions between these molecules and sodium. And we also try to get some, to contribute somehow to explanation of these measurements. On the other hand, aluminum fluoride experiment is on the a bit starting stage, but this is the electronic structure of this molecule. And you can see, as I mentioned, that the structure of these 3 dominant electronic states is highly diagonal. It means that they really are aligned, the minima are aligned, and at the same time, the Frank-Condon factors between different lowest vibrational states of these 3 electronic states are really close to 1, would make it perfect for laser cycling, because having just 1 or maybe 2 repumping lasers, we can have really perfect and close cycle for obtaining ultra-cold molecules. And I'm really optimistic that within next 1 or 2 years, the group in Berlin will have ultra-cold aluminum fluoride molecules and can proceed with other exciting measurements. Okay, so before I will present our numerical results for these 2 molecules, I would like to give the brief summary of method that we use for these two systems, because they are quite similar. So of course, as you can imagine, having 14 or 22 molecules, the full configuration interaction calculation or exact diagonalization or just exact calculations are infeasible. So some approximate methods has to be used. And our approach is based on the composite approach where we combine different contributions at different level, trying to get all of them as accurate as possible. So as always, we have to calculate the leading part of the interaction potential using some relatively accurate but feasible scheme. So usually we start with the couplet cluster method with single and double excitation and triple excitations included perturbatively, and then in the smaller basis sets in this composite and hierarchic way, we try to include higher level excitation up to quadruple and pentuple contributions. We also try to estimate the leading relativistic effects for the interaction energy in these systems using perturbation theory, we also estimate, because it will be just rough estimation of the leading QED correction, rather to realize how far we are from the level where we really can start thinking about cross-checking the theory for QED effects in this kind of molecules with cold molecule measurements. We also look at the diagonal adiabatic or Born-Oppenheimer correction, but depending on the system, it can be relatively small. For the non-relativistic interaction potential, we use the standard single electron basis sets and Gaussian basis sets, and we correct the basis set superposition error by using the supermolecular method. And then the different higher corrections we calculate in this manner, where we, for example, can calculate the importance of the full triple or quadruple or higher corrections in the smaller and smaller basis sets, because of course the computational time is larger and larger. But anyway, we are able to go to quite high orders of the couplet cluster in this hierarchy of couplet cluster methods applied with different basis sets from the Dunning series. We also developed, if needed, for example, basis sets up to 6 zeta quality for this molecule that I mentioned. And of course, we also interpolate the obtained energy to the complete basis set limit using the standard ways, or we also apply sometimes, depending on the state and the problem, the mid-bond. But for example, for aluminum fluoride molecule, the interpolation, the complete basis set limit works perfectly. Okay, so for relativistic effects, we also use the standard in quantum chemistry approach based on the Bright-Pauli decomposition of the Bright-Pauli Hamiltonian, where we have 4 terms. We have the mass velocity term, 1 electron Darwin term, 2 electron Darwin term, and we use it how it is implemented in the CFUR program. Then for the QED correction, we use this approximate formula known already in the literature, where we can relate the leading QED correction, the lamp shift, proportional to the 3rd power in alpha in the quantum chemical, not physical notation, with the 1 electron Darwin term, with this molecular beta logarithm. Of course, this is very approximate approach, and the molecular beta logarithm has to be also approximated because it's very hard to calculate. But our goal is really to get the order of magnitude and get the estimations how important these corrections can be, and should we really be worried about this in our considerations. We also look at the adiabatic, the diagonal Born-Oppenheimer correction, and this is obtained with this is of course the correction due to the action of the kinetic energy operator of the nuclear motion on the electronic wave function. Okay, and once we have the full interaction potential, then we can calculate the scattering and rovibrational spectrum. Luckily, for the diatomic molecules, this can be done numerically exact. So we solve this Schrödinger equation for the nuclear motion using, for the scattering state, the Numerov method, and for the bound state, the nonlinear discrete variable representation. In this, we use nonlinear DVR because this allows us to address also the weakly bound states in the molecules. As I mentioned, luckily, for the simple diatomic molecules, or for all diatomic molecules, the rovibrational structure can be calculated exactly. And here maybe I would mention and introduce that for ultra-cold temperatures, when we look on the scattering wave functions, they have the form of the sine function with some shift, right? And this shift of the asymptotic form of the scattering wave function ultra low temperature can be called the scattering length, and this scattering length parameter is extremely important for all ultra cold physics experiments, because this gives all the information, all the influence of the short range physics or the collision physics on the interatomic interaction on many body physics on the realization of cold atom experiments. Okay. So now, having told this introduction, I will present the results for our 2 molecules. So first, lithium-sodium molecule in the lowest triplet state. So here I presented the interaction energy for the state obtained at different levels of theory. So of course, at the Hartree-Fock level, because this is the van der Waals complex in the spin polarized state, there is no bonding at all. It's not surprising. Maybe surprising is that if we apply, for example, configuration interaction method with single and double, or even with the Davidson correction, the performance is very poor. Similarly as the perturbation theory, which usually approximate couplet cluster result much better. Here, it really fails. And then, of course, once we go to the couplet cluster hierarchy, we start to converge to the accurate interaction energy. We can also we see that by comparing the configuration by single reference configuration interaction with the multi-reference configuration interaction, we see that, of course, the multi-reference nature, or in the other words, the correlation of the monomers is very important. But applying the hierarchy of the couplet cluster is much better than multi-reference configuration interaction, because we can have much better control over the convergence and accuracy of our calculations. So here in the inset, I compare the results of our ab initio calculations with the experimental potential, that was experimental fit that was obtained by fitting the numerical curve to vibrational spectrum, and our final interaction energy. And as you can see here, surprisingly, the final energy curve, this black curve, including all higher correction that I will tell in a moment, overlap very well with the couplet cluster, with the CCSD parenthesis T results, right? So if we would calculate only the non-relativistic interaction energy at the CCSD parenthesis T level, then we would surprisingly get perfect agreement. And this shows that we should always be very careful in quantum chemical calculations for larger systems or intermediate size systems, not to be too happy with the perfect agreement with the experiment, because it can be accidental, as it would be by stopping the calculations at non-relativistic couplet cluster CCSD parenthesis T. The second thing that you can see here is the comparison between the experimental fit and the theory fit. As you can see here, the depth, the minimum, is very close to each other, but there is apparent shift in the positions of these two curves, and this we will analyze later as well. And the second thing that you can see on the main plot is that the experimental fit, especially close to the classical turning point, diverge much more from our theory predictions. Okay, so before I will focus more on the comparing and cross-validating experimental curve, I would like to present the small correction that we included. So we included the relativistic corrections. So as you can see, relativistic correction here is around 1.5 wave number out of 250 wave numbers, what is much below 0.5%. But as I mentioned, because our goal is to get really spectroscopic accuracy, we need to include it. And at the same time, here we can see an explanation of why we get this perfect accidental performance of the couplet cluster parenthesis T, because the relativistic correction and the full triple correction in this approach, they have very similar order of magnitude, they have very similar size, but opposite sign. So somehow the inclusion of full triple correlation quite well cancel the relativistic correction. Plus here we also show that it's important to include the correlation of the 1s orbital of sodium, which is usually not correlated in the Dunning basis sets. And then in the second plot, we show some smaller corrections. And while the corrections in the upper panel, they have to be included because they are larger than uncertainty of the leading term and these corrections on its own. The second panel is rather for evaluating the importance of different corrections, because as you can see, the value of the QED correction or adiabatic correction or the quadruple correction or the higher corrections is rather small. It's on the order of 0.1 wave number. What is smaller than uncertainty of the leading non-relativistic term or relativistic correction, but it's as you will see in a moment, it's not far away from the point where we have to start to include these corrections. Okay, so here in the table I show the convergence of the dissociation energy and the well depth for the lithium-sodium molecule with the employed interaction potential. So again, at the bottom, we have the experimental value. So as I already mentioned, we have this accidental perfect agreement or quite well agreement with the capped cluster parenthesis T, what we should be worried. Then we include the triple interaction, we include the triple correction, full triple correction, we go to deeper potential, we higher again deeper potential, then relativistic correction counterpoised, and then there are some small QED and adiabatic corrections. So as I mentioned already, the QED and adiabatic correction here, they are factor 5 smaller than the uncertainty of the leading term. So it means that, of course, we cannot yet, by comparing the experimental and theoretical value, tell anything about this, but we see that if we improve the accuracy of the leading terms by the order of magnitude, by the factor of 10, then we will be in the range where we can start really validating if this kind of approach for calculating relativistic and QED effects in many electron molecules is reasonable, or if we should really think about better schemes. I mean, for sure, we can think about better schemes, more accurate and more exact schemes of including these effects in ab initio calculations for this kind of molecules. So at the end, we got the quite good agreement with a bit better agreement than our estimated uncertainties. But again, we should be always aware that accidental agreement can happen. And the second very important parameter that we are able to get from this calculation, the scattering length. And again, as you can see, once we compare the scattering length obtained with potential as different level of theory with the experimental value, we see that this perfect agreement already initially. Then, of course, it's worse and worse. But again, once we include all the corrections, the agreement is quite okay, or even quite good. So we are also able to estimate the uncertainties of the scattering length. And in fact, this calculation for the lithium-sodium molecule is the first ever prediction of the scattering length for alkali metal atom collisions with controlled uncertainty. So as I didn't mention it, but now I'm telling, calculating the scattering length is extremely challenging because it's highly sensitive to the accuracy of the interaction potential, because the quality of the calculation of the scattering length does not depend on the accuracy of the depth of the potential, but on the accuracy of the last weakly bound state, which is much more challenging to get. But anyway, here for the first time, we were able to get for any alkali atom system. And as you can see here, that of course, the relativistic effects are huge compared to typical uncertainties of the experimental measurements. And in fact, this measurement is a bit old, and typical accuracy of the cold atom collision experiment will be below 1. So it means that in typical collision experiments, we can get the scattering length with accuracy below 1 Bohr. And this can be compared to the importance of the QED and adiabatic effect. And as you can see, the QED and adiabatic corrections, they change the scattering length by around 2 Bohr, right? And so it means that these corrections, they contribute more that the accuracy of the scattering length that can be get from the experiment. So it's really also opens the way for ways to make the precision tests of the many electron ab initio calculations for small molecules. So as I mentioned, there was this discrepancy between our theory potential and the experimental fit. So here I presented the difference between the experimental fit to data and our theory. And as you can see, and this shadow area shows the uncertainty of our calculation. And so you can see that the difference is much larger than the uncertainty of our calculation. But we are quite sure about the correctness of our estimation. So we try to understand what was wrong in this experimental fit. And luckily for us, for explaining this disagreement, in the experiment, only states with J equals 0, so only states without rotation were measured. So it means that once fitting the curve, only the vibrational state without rotation were used. And in this scenario, it's impossible to exactly locate the vibrational states. And in the experimental fit, they use the old theory, less accurate equilibrium distance. And now, if we use our new theory equilibrium distance in the experimental formula for this potential, we see that we decrease the difference between our theoretical potential and this new corrected experimental fit is much smaller. Still, it's larger than uncertainty than uncertainty predicted by uncertainty. But we can proceed with this analysis. And for example, if we look on the vibrational energies, then we see that in our calculation, the root mean square deviation of the vibrational state and vibrational excitation energies like here, we can contrast it with what are the values for the experimental fit. And of course, for experimental fit, it's a bit better. So factor 3 errors are smaller, although surprisingly, for the excitation energies, the root mean square deviation is larger. So it suggests that really they didn't have systematic error cancellation, and somehow they didn't use really justified by physics shape of the potential. So by making very simple test, by rescaling our potential by small factor, what we can get, we can reduce the difference between the vibrational energy obtained with our potential and experiment to much smaller numbers than what was done with experimental fit, showing that with our slightly modified potential, we can get much better explanation of the experimental values. And now, if we compare this slightly scaled our potential, which reproduces vibrational states much better than experimental fit, still we have huge difference. But now our slightly modified potential reproduces the vibrational spectrum much better than experimental fit. And this, I think, finally confirms that really our potential has more accurate shape. So again, the volume and spectrum and position of the vibrational states is reproduced quite okay with the experimental fit, but its location and shape is a bit wrong. So it's too deep at short distances, closer than equilibrium. Equilibrium is around here, and too shallow at larger distances. So I think that my time is really close to end. So I think that I will maybe present only one plot and skip to the conclusions. So we also studied in the very systematic way aluminum fluoride molecule in the both ground state and triplet state. And here, just for 20-second comparison, you can see that the behavior of the convergence of the interaction energy for aluminum fluoride molecules is completely different because the energy scale is completely different. We are now 2 orders of magnitude high. We have interaction and we have the binding energy 2 orders of magnitude higher. But the errors will be also 2 orders of magnitude higher. The corrections, small corrections, will be 2 orders of magnitude higher. But at the end, the relative accuracy of our calculations will be very similar. And we hope that with our calculations, we also can guide the ongoing experiments. Okay, so I will now jump to the results, to the summaries, which I also skip. And I will thank you for your attention. And hopefully, I will be happy to answer your questions.
Thank you, Michał, for your presentation. Now it's time for questions. So, are there any questions? Grzegorz has a question.
Michał, in the papers you show, you didn't separate, in a separate at least, the contribution of retardation.
Mm-hmm.
Is it important for this sodium lithium dimer, because it was on one hand it's weakly bound, on the other hand the minimum is rather close. So what's did you include it, and what were the results?
No, so in principle we don't include it, but I think it's on the it can be important when we are including the QED correction, but definitively it's much smaller than relativistic correction, the leading relativistic correction. As you can see, our goal was rather to estimate. So I mean, this was to get the relativistic correction with some 20% uncertainty, and for the smaller corrections was rather to get estimation how they are important, because anyway they were smaller than uncertainty of the leading terms. So it's true that that retardation should be included, but I think that our tests or by comparing to other systems suggest that it should be smaller than, it should be on the order of QED or smaller, or it should be, in fact, it should be included in QED correction.
Okay, for the questions, let me then, if I don't see question participant, let me ask the question. So you are one of the few to include the QED effects, so I am not sure how did you calculate beta logarithm, for example?
Yes.
For
So no.
how many electrons? How many electrons do you have here?
No, we have, yes. So we have, so as I mentioned, so the molecular beta logarithm is approximated by the atomic beta logarithm.
Ah,
right?
now I understand. Okay.
Yes. So,
and
so
D1 is the electron nucleus delta.
Yes, exactly. So D1 is the 1 electron Darwin for atom, and these are the beta logarithms for atoms known from other calculations from other.
Yeah, no, I understand. I understand. Okay.
Yes, so I'm sorry.
And
yeah.
how did you calculate the Araki-Sucher term?
No, we don't include Araki-Sucher term. So we only.
I don't understand.
No, we only.
You don't include in the sense, so.
We only include this.
You don't include because it is small, or what?
Because we cannot. We don't know how to include it for the.
Okay.
For this.
So Michał, so you still claim that you calculated QED effects?
No. I claim that I estimated leading QED.
Now I understand. Okay.
Because
now I understand.
As I was repeating, the value of it's anyway smaller than uncertainty. So of course the goal is to increase the accuracy of the leading non-relativistic and relativistic, and then of course.
Okay, because Araki-Sucher term can be large for the weakly bound molecules. I mean.
Okay. But this is exactly something that we would be very happy to cross-check once we get higher accuracy.
Yes. So you have to
this is only estimation and somehow playing and checking when and what we have to do to start trying to verify the QED theory of many electron molecules with cold molecules or cold collisions.
Very good. Let me check if there are further questions from participants. There's another from Timon Kilich from Gdańsk Technical University. How did you it disappeared. How did you manage to calculate beta logarithm for atom? Oh, okay, it's exactly the same question as mine. How did you manage to calculate atomic beta logarithm? So no, the A and B.
They are taken from literature. So for lithium, I took it from.
Once again, you repeat.
Yes, for the lithium atom, we took it, for example, from your work.
Yes, because we calculate for sodium.
And for sodium, there are estimates on the mean field level. There are I think that.
Who has calculated it?
There are some models, kind of, it's rough models again, but I think that there are some models, for example.
No. Don't answer in this way. Be more specific. How one can calculate beta logarithm for sodium?
I think that in, for example, this work that we cite here, right? If you make the approximation that you have effectively 1 electron sodium molecule, 1 valence electron, and then you treat the rest in the approximate way, then you get the estimation of this. I think this were the. Okay,
so now now I have even better picture of how did you calculate beta log. So
this is exactly
how I understand.
Really rough estimation. So in fact, our QED term has the uncertainty like 100% because
Michał, I think one of the challenging thing in this small molecular system, because sodium lithium is still a small molecular system, is to calculate beta logarithm, because this Araki-Sucher term is relatively easy to calculate. I would say easy. But the calculation of beta logarithm is a challenge. So I would say it's a long-standing problem.
Absolutely.
For years, how to include beta logarithm. Because I would say you may use the hydrogenic one, because all this beta logarithm doesn't differ much from the hydrogenic one.
Exactly.
So if we want to go beyond the hydrogenic one, it is a challenge. I would say it's a challenge for next 10 years in quantum chemistry. I would say the purpose of this conference also to give some problems which young students or young scientists can solve. So one of the problems is the accurate calculation of QED effects, because what you have done is a very approximate one. I mean,
absolutely,
because you have in mind that the accuracy of experiments is not very high, so you adjusted your calculation accuracy to the experimental one.
No, experiment is much more accurate. Just we have problem that we don't know yet how to calculate more accurately the leading non-relativistic terms, because it
yes,
seems
but this is somehow okay. But you know, about the leading non-relativistic term, I think there are about 1,000 or several thousand chemists working on it.
Yes,
I mean, because there are various methods. But on the beta logarithm, it is you and maybe Timon Kilich, maybe someone else.
Yes.
Just you can count them using fingers. Good.
Yeah, no,
Are there many further questions?
So exactly this was the goal, to collect all the known things and to present
It's very good.
how to proceed with this kind of
Yeah, I mean, we have obtained the highest accuracy. Yes. I don't see further questions, so let me thank you once again for the excellent